Hello children, in today's lecture I will discuss about grouping of capacitors, combination of capacitors. Before that, you should think that what is the need of combination of capacitor? Why do we combine? Why do we group capacitors? Let us take an example. Suppose you have 10-15 capacitors of different capacitances, but you require a capacitor with capacitance which doesn't match with the capacitance of the available capacitor. What will you do? Will you go to the market and purchase another capacitor of the capacitance as per your requirement, or you will use the capacitors available to you? Obviously, at first you must try to use the capacitors available to you, and for that purpose combination of capacitors is required. In class 10 you learnt about combination grouping of resistors. As in case of resistors, capacitors can also be combined in three different ways. First is called series combination, second is called parallel combination, and third is called mixed combination. So let us start with series combination, grouping of capacitors, grouping of capacitors. First type of grouping, first way in which we can combine the capacitors is called series combination. Series combination. You see, how can we combine the capacitors in series? You already know capacitors have two plates. Suppose this is a capacitor. Its capacitance is C. It has two plates. There is another capacitor. Its capacitance is C1, its capacitance is C2. It also has two plates. If one plate of both the capacitors are connected together and the other plates are connected to different points, then they are said to be in series combination. Suppose this is connected to the positive potential and this is connected to the negative potential. This is connected to the negative potential and the potential difference between these 2 points is V. You can also put a cell across these 2 points, but I have taken V, potential difference. This is positive, this is negative. Is it clear? Now see, if this plate will be connected to positive terminal of a cell, or it is connected to the positive potential, then it will become positively charged. And suppose the charge on this capacitor, so one plate is plus Q. Obviously due to induction this will be minus Q. You see from here, this is minus Q, this will be plus Q. So you can understand that it will be more easy if I will connect it to the cell. See, then you will easily understand. So positive terminal plus Q charge, negative terminal minus Q charge. So what are you observing here? You know net charge on a capacitor is 0. So plus Q minus Q 0, plus Q minus Q 0. Another thing is that charge on a capacitor means charge on the positive plate of the capacitor, not net charge. So charge on the positive plate of this capacitor, that is charge on this capacitor is plus Q, and charge on this capacitor is also plus Q. Although their capacitances are different, their capacities are different. So one thing you must learn here, that when two or more than two capacitors are connected in series, the charges on each and every capacitor remain same. Means equal charges are observed at each of the capacitors connected in series. Now suppose this is a point A, this is point B, and this is the point C. So A and B are at different potentials. You see how? Because A is connected to this positive terminal and B is connected to other terminal. So A and B are at different potentials. In another way, you can also understand A is connected to positive plate and B is connected to negative plate. So A and B are at different potentials. The potential at A minus potential at B is the potential difference between A and B. That is also equal to the potential difference across the capacitor with capacitance C1. So this is V1, potential difference across A and B. And this is V2, potential difference across B and C. Means potential difference across capacitor with capacitance C2. So you can write V1 as VA minus VB. It is equal to V1. You see, you can write VB minus VC. VB minus VC is equal to V2. And whenever you will add these two equations, you will have VA minus VC. And VA minus VC is equal to V1 plus V2. You see it here now that V1 plus V2. Now VA minus VC, you see VA minus VC means potential at A minus potential at C. Potential difference between A and C, and potential difference between A and C is V. So this VA minus VC can be written as V is equal to V1 plus V2. Have you got? V is equal to V1 plus V2. Now, if you will replace these two capacitors by a single capacitor with capacitance C and get it connected to the same cell with potential difference V, and charge on this capacitor C is Q, then this single capacitor is said to be equivalent capacitor of these two, and this C is called equivalent capacitance of C1 and C2. Have you got? Now see, from this diagram, V, you know Q is equal to CV. So V is equal to Q by C. V is equal to Q by C. It is equal to V1 charge is Q and capacitance is C1. So this is Q by C1 plus V2 means Q by C2. Q by C2. Q can be cancelled out and you will have 1 by C is equal to 1 by C1 plus 1 by C2. As this is the equivalent capacitance for the capacitors in series, so you can put a subscript S so that you can easily remember the formula. It will become 1 by CS is equal to 1 by C1 plus 1 by C2. 1 by CS is equal to 1 by C1 plus 1 by C2. So this is the equivalent capacitance. Now see, what can you conclude from these? First thing is that the charges on each and every capacitor in series remains same. Second point, sum of the potential differences CV1 plus V2 across the individual capacitors in series is equal to net potential difference across the combination V. So 2 points should be remembered here. Is it clear? 2 points should be remembered here in series combination. Now you have to learn about parallel combination. So let us discuss parallel combination now. See parallel combination. In parallel combination, what we have, parallel combination, suppose you have two capacitors, these two are the capacitors. You connect one terminal of both the capacitors together and other terminal of both the capacitors together. That is, one terminal of both the capacitors are connected at one point and other terminal of both the capacitors are connected at another common point. Then this type of combination is called parallel combination. After then this is connected to positive terminal of a cell and this is connected to the negative terminal of the cell, positive and negative terminals. You see now. Suppose the potential difference for this cell is V and it supplies positive charge. Suppose the charge on this capacitor is capacitance C1 is Q1 and for this capacitor with capacitance C2 this is Q2 and negative charge here minus Q1 minus Q2 and this is point A and this is point B. Now see, A and B are 2 points between which C1 is connected. So potential difference across C1 is supposed to be V1 and that across C2 is supposed to be V2. You see here VA minus VB is V1. VA minus VB is V1. VA minus VB is V2. And VA minus VB is V. You can get surprised that why are we taking VA minus VB V1, VA minus VB V2 and VA minus VB V? You see VA minus VB is V1, VA minus VB is V2 and VA minus VB is V. That is all V1, V2 and V are equal. Therefore V is equal to V1 is equal to V2. What can you conclude from here? What can you conclude from here? That equal potential differences are observed across each and every capacitors connected in parallel. Equal potential differences are observed across each and every capacitors connected in parallel and that is equal to the net potential difference of the combination. Now let us see the expression for capacitance. Here you see expression for capacitance. If you will use a single capacitor in place of both the capacitors and connect it to the same cell with potential difference V and it draws a charge plus Q in such a way that this Q is equal to Q1 plus Q2. Q is equal to Q1 plus Q2 because whatever charge is supplied by this cell that is distributed into two parts. You see that is distributed into two parts here, Q1 and Q2. So substitute the value of Q here. You see Q is equal to CV. Suppose C is the equivalent capacitance. C is the equivalent capacitance. So Q is equal to CV and Q1 is C1 V because V1 is also V plus Q2 is C2 V because V2 is V and from here you can see that V will be cancelled out and ultimately C will be equal to C1 plus C2, as this is the equivalent capacitance in parallel combination. So you can write it here Cp. Is it clear? Now let us discuss two things here. First thing is that we have series combination. In series combination, equal charges are observed on both the capacitors, but in case of parallel combination, equal potential differences are observed across the two capacitors. In series, sum of the potential differences across the individual capacitors is equal to net potential difference across the combination, and in parallel, sum of the charges on the individual capacitor is equal to net charge supplied by the capacitor. Third type of combination is mixed combination, in which we have some of the capacitors connected in series, and then those group in series are connected in parallel, or vice versa. Means you can have some capacitors connected in parallel, and after then those groups will be connected in series. We will not discuss here any special formula for mixed combination, because it will depend upon the situation. In some books you can have the formula, but you have not to learn them. That will depend upon the situations. So these were the grouping of capacitors, combination of capacitors you already learnt. In the next class will be with the other topic. Thank you.